Hello, my name is Darina. I am a research assistant here at the Institute of Smart Systems and Artificial Intelligence. In this tutorial, you will learn about facial landmark localization in visual and thermal domains. The first part is the introduction. You will also see a brief code demonstration of facial landmark detection on visual images. So, what is the facial landmark detection? Facial landmark detection is a computer vision task used for finding important regions on the face, such as the eyes, nose, lips, jawline. You might be wondering, why do we even need landmark localization? In fact, landmark detection can be further used for face recognition, expression recognition, face tracking, drowsiness detection, 3D face modeling, and face beautification. You might be already using it while unlocking your device with Face ID or when using some filters for social media stories. However, facial landmark detection is not quite straightforward because of various occlusions such as glasses, hands, masks, various illumination conditions, the head pose, and facial expressions. It's even harder for a machine because all it can see is a matrix of numbers. For a machine, or to be more precise for a machine learning model, the facial landmark detection is defined as follows. Given an input image, which is basically a matrix of intensity values, we firstly find a bounding box around the face. It's called face detection. If you want to learn more about face detection, you can watch the previous videos in this series. After we obtained our region of interest, we run the facial landmark detection model, which outputs the coordinates of facial landmarks. Various methods were introduced to tackle the problem. Early techniques are Active Appearance Model, AAM, and Constraint Local Model, CLM. AAM is a statistical method that finds shape and appearance coefficients together with defined transformation parameters that best fit the input image. CLM methods are probabilistic methods that utilize global facial patterns and local to each landmark appearance information for inferring the landmark locations. Both AAM and CLM are considered to be holistic methods because they capture global facial shape patterns. However, CLM is an improvement upon AAM because local appearances around landmarks are also considered. This helps with illumination and occlusion problems. More recent approaches are the regression-based methods that directly learn the mapping from image to landmark locations. In contrast to the previous two, the regression-based methods do not predict holistic facial shape. They are implicitly learned during the training. We can subdivide regression-based methods into direct methods, cascaded methods, and deep learning methods. In direct methods, the coordinates of facial landmarks are not initialized beforehand, and landmarks are directly predicted from an image. These methods are often not robust for occlusions. In cascaded methods, some initial positions are given to a model, and landmark positions are refined in subsequent steps. In deep learning models, different neural network architectures are constructed to find the facial landmarks. They might be robust and accurate, but they are processed on graphics processing unit, which might be problematic for some embedded devices. Therefore, using cascaded regression methods which run on CPUs might be more feasible. In general, these machine learning methods especially benefit from the availability of large datasets. On the screen, you can see several most commonly used datasets for facial landmark detection. They differ in the number of landmarks and their configuration. For example, the Helen dataset is annotated with 194 landmarks, while LFPW is annotated with 29 landmarks. Moreover, some datasets are collected in the laboratory condition, while others are collected from the internet. Now, we will demonstrate how you can find the facial landmarks on visual images. In particular, we will be using the method proposed by Katsumi in the paper 1 millisecond face alignment with an ensemble of regression trees. The main idea behind it is to use gradient boosting for the learning ensemble of regression trees. It falls under the category of cascaded regression methods. The method handles missing or partially labeled data. Most importantly, it can accurately estimate the positions of facial landmarks in real time on Central Processing Unit CPU.
The method is implemented in the face recognition library, which itself is based on the general-purpose library delib. First, you'll need to install delib, which you can do with command pip install delib. Second, you need to install face recognition library, which you can do with pip install face recognition. The code I'm using for demonstration also utilizes the OpenCV library for loading and displaying images, but you can use any other library for these purposes. As can be seen from the screen, I also import argument parser and time libraries. First, we have to create argument parser. Our Python script will accept the following arguments. Image is passed to image on which we want to find landmarks. Face model is the model we are going to use for face detection. As you may know from the previous tutorial on face detection, the model can be either HOC or CNN. We also parse the upsample argument to face detector. The most important argument for landmark detection is land model. It can be either small or large. The large model finds 68 landmarks, while small model finds 5 landmarks. After setting up the parser, we read the image. I use the CV2 imRead function for this purpose. Then I perform face detection. In fact, you can skip this step. By default, landmark detector will use HOC face detector with upsampling rate 1. However, if image contains multiple faces, I would recommend finding faces first and then passing them to landmark detector as I am doing in the line below. The command for facial landmark detection is face recognition, face landmarks. You are required to pass the image. Passing face locations or model is optional. By default, 68 landmarks will be predicted. The code around landmark detector simply calculates time spent on detection. The last thing to do is displaying image with predicted landmarks. We are doing it in this block of code. The reason why we use such nested structure of for loops is that landmark detector returns list, each element of which is dictionary of landmarks for only one face. The dictionary keys are specific landmark positions like chin, left eye, right eye, etc. So you can rewrite code to predict only the landmarks around the eyes, for example for drowsiness detection. Here we just take all landmark values. The coordinate of landmark is tuple of x and y value, which we use to draw specific point on the image. Now let's run the code. As you can see from the terminal window, I type python predict landmarks.py and I pass as arguments my image example1, HOC face detector, upsampling rate 2, and I'm using large landmark detector model to predict 68 landmarks. Here's our output. Now let's try harder example. For that purpose, I am changing my image to example 2, and we could use CNN or HOC. Let's use HOC with upsampling rate 2 and large landmark detector model. Here's the output. You could use CNN, but it will take much more time. Thank you for watching this tutorial. Have a nice day.